Hi everyone, welcome to Education Hub Zone. So today we are going to discuss about physical chemistry. The topic is thermochemistry. Before getting started, please don't forget to like, share and subscribe on my YouTube channel for more upcoming videos. Okay, let's get started. Thermochemistry. First of all, what is thermochemistry? It's the branch of physical chemistry which deal with the heat changes during the chemical reaction. In chemical reactions, there are two types of heat changes. A. Endothermic reactions. B. Exothermic reactions. Okay, let's start with endothermic reaction. It's the type of chemical reaction which proceed with the absorption of heat energy. Or it's the type of reaction which absorb heat from the surrounding. Let the added heat be plus Q. A and B be reactants, C and D be products. So A plus B plus Q react to produce C plus D. For endothermic reaction, the heat of reaction is always positive. Exothermic reaction is the type of chemical reaction which proceed with the evolution of heat energy, or is the type of reaction whereby heat is released to the surrounding. A plus B react to produce C plus D plus heat. For exothermic reaction, the heat of reaction is always negative. Below are the energy level diagram for exothermic and endothermic reaction. For exothermic, the reactant lose heat to produce product. For endothermic, the reactant gain heat from the surrounding to produce product. Below are energy profile diagram for endothermic and exothermic reaction. Activation energy is the minimum amount of energy required by the reactant to initiate the reaction. Activated complex is the state at which the reactant has necessary energy in order for the reaction to take place. Note: heat evolved at a constant pressure and a constant temperature is equal to enthalpy change. Heat capacity, denoted by capital C, is the amount of heat required to raise the temperature of the system by 1 degree. Its formula is heat capacity equals to heat absorbed divided by rise in temperature. Units of heat capacity are joule per degree centigrade or joule per Kelvin. Specific heat capacity, denoted by small c, is the heat required to raise the temperature of 1 gram of a substance by 1 degree. Specific heat capacity equals to heat absorbed divided by rise in temperature times mass. Units of specific heat capacity are joule per degree gram or joule per Kelvin gram. Molar heat capacity, denoted by Cm, is the heat required to raise the temperature of 1 mole of a substance by 1 degree. Molar heat capacity equals to heat absorbed divided by rise in temperature times number of moles. Thermochemical reactions are the type of reaction that involve evolution or absorption of heat. Thermochemical equation is the chemical balanced equation which gives the heat change evolved or absorbed during the reaction. Number 1. Enthalpy of formation. The enthalpy change or heat change when 1 mole of a substance is formed from its constituent element being in their physical state. Standard enthalpy of formation. The enthalpy change or heat change when 1 mole of a substance is formed from its constituent element being in their physical state at standard condition. Number 2. Enthalpy of combustion. If the enthalpy change when 1 mole of a substance is completely burnt in excess oxygen or air. Standard enthalpy of combustion. The enthalpy change when 1 mole of a substance is completely burnt in excess oxygen or air at standard condition. It's Dp. Number 3. Enthalpy of neutralization. If the enthalpy change when 1 mole of hydrogen ion or proton from an acid are completely neutralized by a base, or if the heat change when 1 mole of hydroxyl ion from a base are completely neutralized by an acid. Standard enthalpy of neutralization. If the enthalpy change when 1 mole of hydrogen ion or proton from an acid are completely neutralized by a base at standard conditions. STP. Number 4. Enthalpy of solution. If the enthalpy change when 1 mole of a substance dissolves in a specified amount of a solvent at constant temperature and pressure. Number 5. Enthalpy of vaporization. If the enthalpy change when 1 mole of a liquid is converted to gaseous state. Number 6. Enthalpy of fusion. If the enthalpy change when 1 mole of a solid substance is converted into liquid state. Number 7. Enthalpy of sublimation. If the enthalpy change when 1 mole of a solid substance is directly converted into gaseous state. Note: enthalpy of sublimation is always positive. Number 8. Enthalpy of dissociation. If the heat energy absorbed when 1 mole of a gaseous molecule dissociates to atomic gas. Number 9. Enthalpy of atomization. If the heat absorbed when 1 mole of a gaseous molecule dissociates to atomic gas. Number 10. Ionization energy. If the minimum amount of energy required to remove an electron completely from a gaseous atom to form a gaseous ion. First, ionization energy. If the minimum amount of energy required to remove 1 mole of electron completely from a gaseous atom to form a monopositive gaseous ion. Second, ionization energy. If the minimum amount of energy required to remove 1 mole of electron completely from a monopositive gaseous ion to form the positive gaseous ion. Note: ionization energy is endothermic. Changes heat is always positive. Number 11. Electron affinity. If the energy change when 1 mole of a gaseous atom is converted into gaseous ion by gaining electron. First, electron affinity. If the heat evolved when 1 mole of a gaseous atom gain electron to form mononegative gaseous ion. Second, electron affinity. If the heat absorbed when a mononegative gaseous ion gain electron to form a negative gaseous ion. Note: second electron affinity is endothermic, that is, change in heat is always positive. Number 12. Lattice energy. If the heat or energy released when 1 mole of a compound is formed from a gaseous ion. Number 13. Enthalpy of hydrogenation. If the heat change when 1 mole of unsaturated compound is completely converted into corresponding saturated compound by addition of hydrogen. Number 14. Heat of transition. If the heat change when 1 mole of an allotropic form of an element changes to another allotropic form. Note: allotropy is the existence of element into different physical states. Methods used to determine heat of reaction. Number 1. Direct method by calorimeter method. Number 2. Indirect method by calculation. Number 2. Indirect method. Hess's law of heat summation. It states that heat change during chemical reaction is the same whether the reaction is brought about by a single stage or through intermediate stages. Consider the cycle below. By applying Hess's law of heat summation, heat 1 equals to heat 2 plus heat 3 plus heat 4. Haber cycle. If the cycle which traces energy changes during chemical reaction by converting the reactants into products by different routes. Consider the Haber cycle of formation of sodium chloride. Recall lattice energy. If the heat evolved when 1 mole of a product is formed from gaseous ions. Significance of lattice energy. It tells us whether the product can be formed or not. A. If lattice energy is negative, the product can be formed. B. If lattice energy is positive value, the product cannot be formed. Number 2. It tells if the compound is stable or not. The more negative the lattice energy is, the more stable is the compound. Example 1. What is the heat of combustion of ethoxyethane C2H5 or C2H5? If its standard enthalpy of formation is negative 280 kJ per mole and the heat of combustion of carbon and hydrogen to be 394 kJ per mole and 286 kJ per mole respectively. Solution. Given carbon plus hydrogen gas plus oxygen gas react to produce C2H5 or C2H5 with the change of heat equals to negative 280 kJ per mole. Another reaction is the combustion of carbon. Carbon plus oxygen gas react to produce negative 384 kJ per mole. It is negative because enthalpy of combustion is always exothermic. Another reaction is the combustion of hydrogen gas. Hydrogen gas plus oxygen gas react to produce water with a change of heat equals to negative 286 kJ per mole. It is negative also because it is enthalpy of combustion. We are required to find the enthalpy of combustion of ethoxyethane with the equation C2H5 or C2H5 plus oxygen gas react to produce carbon dioxide and water. First of all, we reverse equation 1, then we multiply equation 1 by 1, equation 2 by 4, and equation 3 by 5. After reversing equation 1 and multiply it by 1, we get C2H5 or C2H5 implies carbon plus hydrogen gas plus oxygen gas with a change of heat equals to 280 kJ per mole. Then by multiplying equation 2 by 4, we get carbon plus oxygen react to produce carbon dioxide with a change of heat equals to negative 394 times 4 kJ per mole. And finally, after multiplying equation 3 by 5, we obtain hydrogen gas plus oxygen gas react to produce water with a change of heat equals to negative 286 times 5 kJ per mole. Then by adding the above three equations, we obtain C2H5 or C2H5 plus oxygen react to produce carbon dioxide and water at the required equation. Then by applying Hess law of heat summation, we obtain heat of combustion equals to 280 plus negative 394 times 4 plus negative 286 times 5, which is equal to negative 2726 kJ per mole. Therefore, the heat of combustion of ethane is negative 2726 kJ per mole. Determination of heat of reaction from bond energies. Bond energy is the energy required or absorbed to break the covalent bond completely from gaseous atom. Example 2. Hydrogen molecule dissociate to produce 2 hydrogen atoms. Example 3. Hydrogenation of ethene into ethane. Reactant to product. Bond breaking. Then there is bond formed. Hydrogen bond from the hydrogen gas breaks to form 2 carbon hydrogen bonds. Then double bond breaks to form single bond. Heat of reaction equals to heat of reactants plus negative heat of products. Example 4. Calculate the enthalpy of hydrogenation of propane at 25 degrees from the following bond energies. Triple bond 833 kJ per mole, double bond 611 kJ per mole, single bond 347 kJ per mole, carbon hydrogen bond 414 kJ per mole, hydrogen bond 435 kJ per mole. Solution. Propene react with hydrogen gas to produce propane. Bond broken, bond formed. Triple bond result to the formation of double bond. 2 hydrogen-hydrogen bond result to the formation of 4 carbon-hydrogen bond. Then double bond result to the formation of single bond. Then the heat change of the reactant equals to 837 plus 2 times 435 plus 611 equals to 2318 kJ per mole. Then change of heat of the product equals to 611 plus 4 times 414 plus 347 equals to negative 2614 kJ per mole. Then heat of the reaction equals to 2318 plus negative 2614 equals to negative 296 kJ per mole. Therefore, the enthalpy of hydrogenation of propene is negative 296 kJ per mole.